Hi everybody. In this video I'm just going to go over what we would have done in class today. I'll try not to make it too long. But the first thing that we were going to talk about today was just going back to what we already talked about earlier in the semester about Chapter 4, which was linear correlation. And we did look at some scatter plots and try to connect them with the linear correlation coefficient. And the letter for this is R. It measures how strong the linear relationship between two variables is. Okay, so here are a couple of scatter plots. And this one, since it's going up as it goes from left to right, would have a positive linear relationship. It looks like there is somewhat of a linear trend there. So for this, the R value would be fairly close to 1. For this one, it looks like a stronger straight line pattern, but it's going down as it goes to from left to right. So this one would have a negative correlation, and the R value is actually pretty close to -1. In this one, the data is all spread out. So we'd say there's no correlation at all, and the R would be 0 or very close to it. And in this one, it looks like there is a relationship, but it's not in a straight line pattern. What we're talking about in this chapter is just straight line type relationships. So for this one also, the R would be very close to 0 because there is no linear correlation between the two. So now what we're going to do is talk about testing for linear correlation. We're actually going to do a hypothesis test to determine whether there would be a linear correlation between two variables or not. Now these hypothesis tests will use basically the same steps as what we've talked about before, but the nice thing in this is that the null and alternative hypotheses are always the same. You don't have to go to a lot of trouble trying to write these because they will always be the same thing. And in fact, for these you can just write them out in words if you like to. The null hypothesis will always be that there is no linear correlation. The alternative hypothesis will always be that there is a linear correlation. If you want to use the symbols, that's fine. The only extra thing that these symbols tell you is since this is a not equal to in the alternative hypothesis, that means it's going to be a two-tailed test. Here's the test statistic formula, and notice this uses R, which is our correlation coefficient. So that comes from our sample data. So once you have your sample data, find the R. You can use that. You can do that using either StatCrunch or your calculator, and we'll look at how to do that with your calculator. So the R goes in here, and the N is the number of data points that there are. So in other words, it's the number of pairs of values that we have. When you go to find the p-value, since this says t right here, that means we're using the t distribution, and we'll use n-2 degrees of freedom. And remember when you're doing that it's a two-tailed test, so you'll find the area under the t distribution and then multiply that value by 2 to get your p-value. So let's look at an example. This data looked at the cost of a slice of pizza versus subway fare. I think this was supposed to be in New York City for specific years. And the question is whether these two things have a linear relationship or not. So first we're going to look at how to find the R value for these two, and then we'll do a little hypothesis test to determine whether there's actually a linear correlation or relationship between the two variables. Okay, so to do this with your calculator, actually the first thing that you have to do, if you haven't already done this, is to turn on the diagnostics so that your calculator will actually give you the R value. So to do that, there are a couple different ways to do this depending on what calculator you have. But one way that works for everyone is to go to your catalog. Notice catalog is above the 0. So if you do second and your 0 key, then you get the whole catalog of functions, and we're going to scroll down to the function diagnostic on. So just go through this. It's in alphabetical order down to the D's. Okay, so we want the one that says diagnostic on right there. So when you get to that, just push enter and then push enter again. Your calculator will say done, which means that it has turned that on. Once you turn that on, you don't ever have to turn it off. It will just be on unless you specifically go in and turn it off. Okay, so now what we're going to do is put this data in. We're going to put the pizza into L1 because that's going to be our X variable. We'll put the subway fares into L2 for our Y variable. So to get to your list, remember you do stat and edit. And I already put these values into L1 and L2. So here are our pizza slice costs and here are our subway fares. Okay, then to get anything to do with linear correlation and regression, go back to your stat button, arrow over to calc, and we're going to choose the fourth one on the list right here, which says, this stands for linear regression, and then it has the AX plus B. So we want number 4, and if you've put your X's into L1 and your Y's into L2, then you don't have to tell it anything else. So I'm just going to enter through this. If you have an older version of the calculator, it will just come up on your home screen and say lin reg AX plus B, and you can just push enter. Okay, so here's what it should come up with, and if you turned on the diagnostics, it will give you R squared and R down here. So right now what we're interested in is the R, so that's 0.988. Okay, so now if we're going to do a hypothesis test, we need to go back to this test statistic over here. Okay, so now what we're going to do is put in the value that we got for R here, and then we're going to put in the N value here. We actually had 6 data points, so our N is going to be 6. So we're going to put in 0.988. It's a little bit hard to write with this thing, so I'm doing the best I can. So we've got 0.988 up there, and then here we're just putting in the 0.988 for R down here also. And then down here we're putting in the N, which is 6. Okay, so calculating that, I got 12.8 for my test statistic. Now that is a big value for a test statistic. And remember, we're using the t-distribution. So here's our distribution. 12.8 would be way over here somewhere on the right. So I'm going to put it as far over here as I can on this. Now, since we're doing a two-tailed test, we're just going to look at whatever tail our test statistic is in, which would be the right tail. So we're finding the area in the right tail past 12.8. So we're going to do TCDF, and we're going from 12.8 to the right. And remember, we're using n minus 2 degrees of freedom, so we've got 4 degrees of freedom. Okay, so our p-value turns out to be 1.07 times 10 to the negative 4th. So that's, well, whoops, that's our area under the curve. Our p-value is actually 2 times this, since it was a two-tailed test. So here's our actual p-value. So that's something like 0.0002. Definitely smaller than any alpha that we would normally pick. So the test results here are going to be positive, which means that we do reject the null hypothesis, which means there is sufficient evidence to support our claim of a linear correlation. So again, in these, the claim is always going to be basically that there is a linear correlation, and if we end up with a positive test results, that means there's enough evidence to support that there is a linear correlation. If we ended up with a negative conclusion, that would say there's not enough evidence to show that there's a linear correlation. And here we can also look at our scatter plot. This was our 6 data points, and it does look like they're in a fairly straight line pattern. Okay, here's another example. This was from a study of women drinking cola and how that affected their bone density. So for 15 women, the number of colas they drank per week was recorded, and then their bone density was also measured. Here's a scatter plot of that data. If we went in and put all that data in, it turns out that the correlation coefficient R is negative 0.806. Notice how this is going down from left to right. That's why it has a negative correlation coefficient. And this looks like a fairly straight line pattern, and the R value is somewhat close to -1. So we could probably guess that there would be a linear correlation. But again, we actually want to do a hypothesis test to determine whether that's really true or not. So since we've already have the R value, then again, we're just going to put that into our test statistic formula. So back here, we're going to use our new R value in this formula, and also our N is different. Our N is 15 in this one. So going over here to the calculator, I'm going to put in negative 0.806 for our R value, divided by the square root . So I'm just putting in all of this info. This is one thing to look out for when you're putting this in. If you have a negative R value, still when you square it, it's going to come out positive. So be really careful with your negatives there. And then on the bottom, we're going to have 15 minus 2, so that's going to be 13. Okay, so our test statistic here turns out to be negative 4.9. Now, if we look at our picture, this time our test statistic is on the negative side, so we'll be finding the area in the left tail. So this time we're going to do our TCDF. So we're going to go from a big negative number to our test statistic, which was negative 4.9. And now we have 13 degrees of freedom. And remember, once you get your area, multiply that by 2 to get your p-value. So this time our p-value is about 0.0003. Still very small. So this again would support the conclusion that there is a linear relationship between the number of colas and the bone density. This one is a negative relationship, so as the number of colas goes up, the bone density goes down. Okay, one more example. This one was a study that connected charges for patients with their age. And this was a hospital that was suspected of inflating charges for older patients. So the question is whether the charges went up as the age went up. And this one was put into StatCrunch. There's a StatCrunch linear regression procedure that will give you everything that you need. So this found the correlation coefficient to be 0.194, sample size of 30, and again, we could just put that into our test statistic formula and look at whether we think there's a linear correlation between the two. So if we put this number into our test statistic formula, and our sample size here is 30, so I'm dividing by 28 here. This time our test statistic is 1.05 approximately. Now again, since this is positive, that means that we're going to be looking at the area in the right tail. So we're going from 1.05 for our lower bound to, say, 1,000 for our upper bound. Our n-2 is 28, so that's how many degrees of freedom we have. And again, we're multiplying this by 2 since we have a two-tailed test. So our p-value for this turns out to be 0.3027. That's a pretty high p-value. That would definitely be false when we compare the p-value to alpha, which would give us a negative conclusion, which means there's not sufficient evidence to support the claim of a linear correlation. And if we look at the scatter plot here, it looks like the data is pretty spread out. Okay, so now what we want to talk about is what we're actually going to use this for. If we do find that there's a linear correlation, then what can we do with it? So what we're going to do is find a line that best fits our data, and then we can use that line to make predictions or make estimates for data values that we don't already have. The line that best fits the data is going to be called a regression line, and the equation for that line is just the regression equation. Now remember back in chapter 1, I think it was, we talked about explanatory variables and response variables. Explanatory is the independent variable. That's going to be the x that goes along the horizontal axis. The response variable, or the dependent variable, is y, and that's going to be the one on the vertical axis. And remember back to algebra, when you talked about straight lines, one of the forms for a straight line was y equals mx plus b, where m is the slope and b is the y-intercept. We're going to use the same basic thing, only we use a little bit different symbols. So instead of just y, we're going to have y hat. This means that it's something coming from our sample. Just like p hat represents the sample proportion, the y hat is going to represent a value that we get from our regression line. The b0 in here is actually the y-intercept of the line. The b1 is the slope. Okay, so there's our regression equation again. This is going to just describe the relationship between the two variables that we found. And what this actually does to get the line that best fits the data points is that it looks at the residuals, which is the difference between the predicted values from the line and the actual values that we've observed in our sample. It takes the difference between those and it tries to minimize the sum of the squares of those. Okay, so again, this line just minimizes the sum of the squared errors. Errors and residuals are the same thing. Okay, so the requirements for doing this are that we have to have a random sample of quantitative data. If we look at the scatter plot, we have to be able to see that the points do approximate a straight line pattern. And here also we can do a hypothesis test to determine if there really is a linear relationship or not. Outliers do affect this very much. So if we have an outlier that might be an error, we want to remove it. And if we have an outlier that's not an error, then we want to consider the effect of the outlier and decide whether to include it in our data or not. Okay, so now we're going to go back to our calculator and actually find the equation for the regression line. So let's go back to the pizza and the subway fare. And the same procedure that we did before on our calculator, which was the linear regression one. So this number 4 on this list not only gives us the R value, it also gives us that linear regression line. So right up here it says y equals ax plus b. And notice that in this one, the x term comes first and the constant term comes second, which is backwards from what the equation is in the textbook. But here it gives you the values for the a and the b. So the a in this one is the slope of the line, the b is the y-intercept. Now if this is a line that's going up from left to right that has a positive correlation, then the a is going to be positive. If it's going down from left to right so that there's a negative relationship, then your a will be negative. And here is also the results from StatCrunch. So if we put this into StatCrunch and ask it to do the linear regression, then it also gives us the equation. And notice how it puts it. It just gives us the variables as whatever we named the columns. So in this one, our y was the subway fare. Here's our y-intercept, here's our slope, and the pizza was our x variable. So this is how StatCrunch shows it. So either way, here's what our linear regression equation would look like. Now what that does is that it gives us this line, which goes as close as possible to the data points. And this way, if we have a value that's in between some of our observed values, like let's say that we wanted to know the cost of subway fare at a point when the cost of a slice of pizza was 75 cents, then we would look at the 0.75 right here, would go up to our line, and the y value for that point would be our predicted value for the subway fare. So if we wanted to predict the subway fare when the pizza cost was $1.50, then using our equation, we would put 1.5 in for x, and then we would just figure out the y value. So according to this equation, if the pizza cost was $1.50, the subway fare would be estimated to be $1.45. Now we can only use this equation to make predictions if we've already shown that there's a linear relationship. So that's why we were talking about doing the hypothesis tests. The other thing that's a little bit dangerous in this is if we're going too far beyond the scope of the data that we have. So if we go back to our picture over here, let's say that we wanted to predict this far out into the future. So let's go out here and say, okay, now pizza costs are $5 a slice. Can we still use this equation to predict the subway fare? Not necessarily, because $5 is so far outside the data that we already have that it's a little bit dangerous to assume that it would still have the same relationship. Now, if we decide that our regression equation is not a good model for any reason, then to predict a value of y, the best predictor is just the mean of the y values that we already have. So we would go back to our sample data, find the average of the y values from the data points that we have, and that's going to be the best predicted value for y for anything. If we're trying to predict values of y, we look at whether the regression equation would make a good model or not. If the line graphed in the scatter plot looks like it fits the points pretty well, if we've done a hypothesis test and it shows that there is a linear correlation, and if our prediction that we're trying to make is not too much beyond the scope of our available sample data, then we can use our regression equation because it's a good model. And in that case, we just substitute our value of x into our regression equation, and that gives us our predicted value of y. If these things aren't true, then we say the regression equation is not a good model. Then we just use the average of the y values as our best predicted value of y. For example, in this study that was trying to relate the charges and the ages of the patients, we found that there wasn't evidence to support that there was a linear correlation. So that means that for any age person, the best predicted value of their charges would just be the average of the charges from what we had. So the best predicted value for anybody that went into this hospital would be that their charges would be $7,647.36. That would be the best prediction we could make. Okay, now we want to look at residuals. This is something that is also in Chapter 4, and this does come up on your final because the final goes from chapters 1 through 7. So a residual is the difference between our observed value, so it's something from our sample, and a predicted value that we get from our regression equation. So here's another way to look at it. The residual is the observed value of y minus the predicted value of y. And for predicted value, that's the y hat. So this would be y minus y hat. And here's how we can look at it in a picture. Here's our regression line, and these little blue points are the actual data points that we had. So for this data point, notice that it ends up below the line. That means that the residual is going to be negative because we're taking our observed value of y, which looks like it's 4 right here, minus our predicted value of y, which is the one that's on the line. So 4 minus 9 would give us negative 5. For this one, because the point is above the line, our residual is going to be positive. So again, we're taking the y value of this point minus the y value of this point on the line. This one has a negative value because the point is below the line. This one has a positive value because the point is above the line. And again, when we're finding the regression line, or when we're using StatCrunch or our calculator to find it for us, the line equation that they find is going to be called a least squares line because it's taking the sum of the squares of those residuals and making them as small as possible. Now, when we do a residual plot, that means that we're taking the x values from our data points, and then instead of plotting the y values, we're plotting the values of the residuals. So for instance, if we go back to this picture, if we were going to do a residual plot for this, then for this point, instead of the point 1, 4, we'd have the point 1, negative 5. So we're plotting the x value with the residual value. This point, we'd have, instead of 2, 24, we'd have 2, 11. For this point, we'd have 4, negative 13. For this point, we'd have 5, 7. So here is our original scatter plot for our pizza versus Subway fare problem. So this again has our data points and then it has our line. So notice that for some of these, the residual is going to be very small. This one here, this one, and this one, the points are all very close to the line. So the residuals would be small. And some of these are above the line, and some of them, the points are below the line. So here would be our residual plot. So, but for instance, for the point where the pizza cost was $1, then notice our subway cost was just a little bit above the line. So that means that our residual plot, the point is above 0, it's positive. For this point, the data point was even further above the line, which means the residual is positive and larger. So here it's further above 0 than it was for this one. And notice all the ones where the point was below the line are negative values. So for residual plots, we can look at those and also use those to determine whether our regression equation is a good model or not. If we just have something like this that looks like it doesn't have any pattern to it, then the regression equation is probably a good model. Now this one, notice that there is a pattern in our residual plot. That suggests that the regression equation is not a good model. And in this one, notice how the residual plot starts over here and then it widens out as we go out this way. So again, that would mean it's not a good model. So basically what we're doing is we're starting with a scatter plot. We're doing a hypothesis test and looking at the scatter plot to see whether there would be a linear correlation. If there is, then we would go on and find our regression equation and construct a residual plot, and then we would look at the residual plot to see if there's a pattern there. If there is a pattern, then we wouldn't want to use our regression equation as a model. On our calculator, when we did the linear regression, it gave us r, but it also gave us r squared. So we're going to look at what the r squared actually means. So here's an example of something where we have a regression line and we have our original point that was on the line. So the one in blue is the regression line. The black one is just the average values, the average of the y values from our sample data. So this one just goes straight across horizontally. So we're talking about the difference between our data value and our predicted value on our line. And we're also looking at the difference between our actual data point and the average values for the y values. So that difference between our y value on our point and our average y value is called the total deviation. Now the unexplained one is the same as the residual. So it's the difference between the y value from our point and the y value on our line. The explained deviation goes from the line to the average y value. Now the only thing about that you really need to understand is when we talk about the coefficient of determination, that's the r squared, that's the amount of variation in y that is explained by the regression line. So that's r squared. It's the explained variation over the total variation. And that gives us a percentage of how much of the variation is explained by the regression line. Okay, so going back to our pizza and subway fare costs, we're going to ask what proportion of the variation in the subway fare can be explained by the variation in the cost of a slice of pizza. So we already found our r value. To get the r squared, we just take this and square it. So our r squared would be 0.976. And that means that 97.6% of the variation in the cost of subway fares is explained means it's explained by the linear relationship between the cost of pizza and subway fares. That means the other 2% is unexplained. Here's the activity that we would have done in class today, and you should be able to do this at home or on a computer, wherever. You just have to get into My Math Lab. So if you sign into your MyStatLab, go to the course homepage, click on Tools for Success on the left side of the page, and then under the thing that says Review, there's a link for applets. So click on that applet link, and then you have to scroll down the page a ways and find the correlation by eye applet. That's the first one in this activity. The second one is called Regression by Eye, and it's immediately underneath the correlation by eye applet. Here's what the correlation by eye applet looks like. And basically all this does is it will plot 20 data points for you, and then you can try and guess what the R value is. And if you click down here where it says Show R, it will actually tell you the right R value. And if you get close enough to the correct R value, it'll give you a nice little message here. If you miss it, it'll say something like, sorry you missed it. You can also drag these points around to put them in any kind of pattern that you want. And I think if you just click, it'll actually even add a data point. If you want to get rid of some of them, you drag them over here to the trash can. So you can drag points around, make this into more of a straight line pattern, less of a straight line pattern, anything that you want. Oops, I'm adding data points here and not even meaning to. Okay, so again, if I wanted to try and guess the R value of this, let's say I'm going to guess this is now 0.85. And then if I click on Show R, it tells me, whoops, it tells me the real R value, and I had 2 dots in here, so it didn't even like my value. So let's try that again. Oh, and now I'm too far from the R value, so it said sorry. Now if I wanted a whole new set of data points, I can just click on New Data, and it'll give me another set of data points. So if you want to, you can keep clicking on this until it gets to something you like. Like this one would probably have a pretty small R value. This one would be something fairly close to -1 since it's closer to a straight line pattern. So for this one, let's guess -0.95. Ooh, I wasn't too far off, so it told me great. Okay, so that's what you're going to use for the first part of this activity. And so it just has you try that 2 or 3 times and make a guess. Then for the next part of this, we're actually going to look at linear regression instead of linear correlation. So on this one, we're using the other applet, the Regression by Eye one. On this one is a little bit confusing because what it does, again, it draws a set of data points for you, and then you get to try and guess where the regression line would go. And this, you can drag the regression line, so if you drag the ends of it, then you can drag the line wherever you want. So the one that you're trying to get is the green one. And here it's telling you what the actual least squares regression line would be. So you can kind of see from the numbers I'm getting here that I'm not all that close to it. But I can keep doing this and try to get it as close as possible. Now the other thing, and what we're actually looking at here, is remember that that least squares line is actually taking these residuals, which are the distance from the actual data point down to the point on the line. It's taking those residuals and squaring them and adding them all together, and it's trying to make that sum of squares as small as possible. So here's in the red, if we actually had the real regression line, the sum of squared errors for the residuals would be 341.6. So when you're dragging your green line around, you can look at the effect that dragging it has on that where it says green SSE. And you can try and get that as small as possible, and that'll tell you that you're getting closer to the regression line. So see, by me dragging it around here, I'm not doing very well. I'm trying to find a direction to drag it that will actually make that smaller. So let's try dragging it this way. Nope, that's not working very well. Oh, okay, that's getting better. Okay, so I must be getting fairly close to the actual regression line because that sum is getting pretty close. And now if I get tired of doing this and I want it to actually show me where the regression line is, I can click on Show Regression Line, and there, I wasn't too far off. Now if I want to try it again, I just click on New Data, so it'll give me a whole new data set, and this one, the sum of squared errors is 123.69. So again, I'm going to try and drag my green line around to make the green SSE get smaller. And again, you can see this pattern looks like it's a negative correlation, so we want to make our line so that it goes down. Okay. Oh, there, now my green SSE is getting smaller. And again, notice this is the actual regression line equation. I'm trying to get this one to be fairly close to it. Okay, so I don't know, that looks like that's about as close as I'm going to get. So there, that was pretty close actually. So this is what you're going to use on the second part of this activity. So just go through this and try it. You can just kind of play with this if you want to and see what happens. There's also a part here where you put one point on the graph that's an outlier, that's basically really far away from the others, and you see what effect that has. Now, one more thing about this, if you have problems getting these applets to work, if you're on a computer at ACC especially, then there is another handout that I'll have out on D2L about how you can temporarily get those applets to work. It's a setting that has to do with the security for Java. So I'll also have that handout out on D2L for you.